Ooh, I have some demos for you. Okay. So I went to Heater, got some dry ice. Okay. So this information here was just a recap from yesterday. Anytime we're going from solid, liquid to gas, or anything that's from a low energy state to a high energy state, is that an endothermic or exothermic process? Endo, because we have to put energy into the solid to make it melt, to make it turn to a vapor. So that's definitely an endothermic process. So reverse would be what? Exothermic process, because it has to release energy to get back down to the lower energy states of matter. And notice I'm not saying reaction, I'm saying endothermic process. The process is a phase change, which is not a chemical reaction because that's a physical change. So don't forget, these are all physical changes, not chemical changes. So that's one thing to just remember from yesterday. We're really going to hit the gases hard today because that's our more interesting part of matter outside of corrosive plasma. So along with gases, we talked yesterday about pressure. And pressure today, I'm going to show you how to convert between all those units of pressure, atmospheres, kilopascals, torr, millimeters of mercury, and that was number 26 on your PS, so I know that I need to go for you. But in terms of causing pressure, causing pressure, the only things that ever are going to cause pressure are usually gases. And gases cause it because all pressure is, just if you're just talking about what is pressure in general, it's just collisions with the container wall. Okay, so collisions with the container wall is what's causing pressure. Well, solids and liquids don't really collide unless you shake them, right, with the container wall. Gases naturally do it. So that's what we're going to be referring to as pressure generally. So the word volatile, what kind of compounds do we use to we use the word volatile to describe? Ionic compounds or covalent compounds were volatile? Raise your hand if you say ionic. Raise your hand if you say covalent. Okay, majority rules. The 4 people who voted. Okay, so it is covalent. So things that are covalently bound generally have a low boiling point, and that's simply because they are very easily transitioning from liquid to gaseous state. That's what the word volatile means. And we use volatility all the time. That's what our perfume and deodorant is helpful for because it makes it smell good. It vaporizes very easily. So only really the only molecules that will ever turn from liquid to gas are the ones that have the highest kinetic energy. So I think I maybe told you this example before, but let's say we have we're at Panera, right? We get some soup. Here's our soup spoon and liquid soup. Okay, what is observe the soup. What's happening to it? It's what? It's in a spoon. It's what? It's steaming. What does that look like? Vapors coming off, right? It probably is water, which was the term we used to describe steam. But there's little vapors coming off. Okay, what are the vapors made of? Say again? When you say water, are you talking about liquid or gas? Gaseous water. Okay, so our gaseous compounds, molecules. Well, the gas molecules are increased in kinetic energy. They have a high kinetic energy. So I want you to think about kinetic energy. Generally, things that are moving the fastest have the highest kinetic energy. Do you also think they're the hottest or the coldest? They're probably the hottest, right? So we generally will blow on the soup spoon, and when we blow on the soup spoon, we're blowing away all the things that are high in kinetic energy, and they're gone, leaving the soup nice and cool. So we've blown away all the ones with highest kinetic energy, and the highest kinetic energy carry all the heat. They carry all the temperature. So that's how we actually work with steam and kinetic energy all the time. We try to make things cooler by moving away those hot particles. Okay, so I think enough with that. Let's go to a closed system now. So in this closed system, we have these three containers. They're just at different temperatures, maybe. So only the things at the very surface are able to vaporize because the highest kinetic energy are the ones at the surface because they have more room to kind of play. And you can see all these particles bouncing out of solution. They're vaporizing. Well, then sometimes they'll vaporize and then they'll recondense. That is called physical equilibrium. So it's not here yet because the vaporization rate is bigger. So more of them are vaporizing than condensing in this picture. But here, vaporize, condense, vaporize, condense, vaporize, condense. And that's called equilibrium because there's an equal amount going in and out, in and out. So this is called physical equilibrium, when the rate of vaporization equals the rate of condensation. So just note that whenever You're going from liquid to gas and then back at an equal rate. That's called equilibrium. And we'll talk about like chemical equilibrium a lot more towards the end of our whole big, semester. But physical equilibrium is just phase changes. And the only reason that we talk about this right now is because it's important to boiling point. So, Matt, I need you to boil water like this. Like this, okay. Boil, man, boil. Okay, so as it's boiling, vapors are coming out, right? Right, so why are the vapors coming out? Why does he have to boil it? I mean, why does he have to heat it up? He's heating it up as he's boiling. So to give the water molecules more kinetic energy, but why don't they just evaporate? Why don't they just pop out? It doesn't work like that. Can you tell me why? Dun, dun, dun. What am I? What kind of pressure? Atmospheric pressure. Okay. Okay. He is water. Water. Atmospheric pressure. When the atmospheric pressure is more than the vapor pressure of the water, you stay down. You do not boil. Okay? But once he's equal, he's like, okay, getting kinetic energy here. Got a lot of vapor pressure. It's equal to the pressure. The pressure kind of has to let it through. The atmospheric pressure does in that case. Because it's got so much energy and it can't fight back, it's going to boil. So when they meet, when they are at the same vapor pressure and at the same pressure systems, that's when it boils. So the boiling point is when the vapor pressure equals the atmospheric pressure. And I think this is on PS 13. Am I right? Definition of boiling point. You're like, when it boils. Well, that's a little bit more than when it boils. Duh. Okay, so you want to say when the pressure of the atmosphere equals the vapor pressure of the solvent or water. And that's when the water or compound has enough kinetic energy to get past that pressure put on by the atmosphere. Okay, so that's for PS 13 information. That pressure conversion is the next thing I want to do. And I might skip this for a second. We'll come back. So this is 26. You guys have this? I saw a lot of people had an answer. No work. I need you to show me some information here. Here's what I need from you. This is the, these are equivalencies. 1 atmosphere, write this down, okay? 1 atmosphere is equal to how many kilopascals? We actually talked about that yesterday. 101.3 kilopascals. And that's equal to how many millimeters of mercury? 760, good. And that's actually, let's just stop at those. Those are the 3 most commonly used. These things are equivalent, just like 1 foot's equal to 12 inches equal to so many centimeters. So we can use these as a fraction, as a conversion factor, and convert from one thing to another. But I do want to see that work because I don't know that you're doing it right if I can see your numbers. So a gas has a pressure of 4.3 atmospheres. What is its pressure in kilopascals? And then separately, what's its pressure in millimeters of mercury? So what are we going to start with here to convert? 4.3. So 4.3 atmospheres. And I want to convert to the other unit. So some of you guys may have caught on to this whenever you were looking at it on your in your textbook. But if we're converting to kilopascals, these are the 2 units we're interested in, atmospheres and kilopascals. So we're going to point at those here, and then I want you guys to tell me which one's going to go on top and which one's going to go on bottom if we're using this one and this one. So I heard kilopascals on top, 101.3 kilopascals goes on top, and on bottom, 1 atmosphere, good. And so the atmosphere has gone bottom because it must cancel. Thank you. Go ahead and calculate for me. I don't have my calculator for me. 436 kilopascals. Okay. So some of you guys caught on, it looks like. Let's go ahead and go to millimeters of mercury. I'm going to start off again. Actually, let's start off in the kilopascals. Let's start off in that because I want to show you can do it from any starting point. You don't have to start off in atmospheres. So I'm going to start us off with 436 kilopascals. And I want you to convert from pascals to millimeters of mercury. So which 2 units are we going to use? Right, the second 2. Okay. So what's going to go on top here? 760 millimeters of mercury. On bottom? Good, 101.3 kPa. And that's because these numbers are given in their equivalencies as they are written. So go ahead and multiply by 760, divide by 101.3. What is it? 274? 271 millimeters of mercury. Okay. So that's how we convert from pressure to pressure. We're going to do that a lot today. So I'm just going to get you started. Let's look at PS13. Can you guys switch the person next to you to check PS13? So I want you to mark it right or wrong, and we'll count up how many they got right or wrong. We're just going to quickly check them, like with letters, and then from here. Okay, switch and get a different color. Do gray with if you possibly can. You guys can see up here. So I'm doing this. This is a reading heavy chapter. So if you didn't read your book, it would have been very hard to get this information. So go ahead and check what you need. If you would, please write the right answer on theirs, if you can, because they probably want that for later on in life. Study guide or whatever you're I'm going to scroll down in just a minute. Can I scroll down past the true false? Just about. Okay. I'll come back to the true false if needed. Let me go down to multiple choice. 28 is A. 20. I'm going down the multiple choice. My bad. How many? This was the one that did it have repeats in your multiple choice? Huh? Okay, because this I thought there were some multiple here. Let me actually pull out my actual study guide. I'm doing this from here with no questions. There are some of the free response in some way or form. So, I think I took out the repeats. There were repeats. I don't have my red notebook out right now. So, are there, let's do it this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Are there 13 multiple choice? Okay, let's just go. The first multiple choice. First multiple choice should be A. Second one, D. D. C. B. C. A. B. A. B. B. C. C. Okay, so scores are, and you guys don't need to write a score on the top. Give that back to the individual. This is good for studying. I'll answer questions after you've had a chance to look back at them, probably tomorrow. Okay, so give them, and I will go back to the false true or later. I'm spending a little bit of time there, so we can move on. So give that back to the individual, keep that for safekeeping. And I got to make some choices here. So let's see how long it takes us to go through the initial pressure information. Then we might do an activity that will reinforce that. Ladies, Nicole, can you guys finish checking that later? Okay. So with pressure, we've dealt with pressure all of our lives, right? We talked yesterday about on top of a mountain at a high altitude. What was the pressure differential? Was it higher or lower? Much lower because there's less air pushing down. Up an airplane, you have the top of your ears to create some pressure equilibrium. Balloon, what's so important about balloons? What's so cool about balloons? Okay, why do they float? So how much does helium weigh? How much does helium weigh? Look at the periodic table. 4 grams per mole, right? Air. What's air primarily made of? Nitrogen. How much does nitrogen weigh? Nobody said it right. I'm waiting for it. 28 grams per mole because it's diatomic nitrogen. You do have to double its mass. So helium weighs much less. It rises. The air stays where it is. Soda cans. What do they do to it to make it nice and bubbly? They carbonate. They pressurize it. And so whenever they pressurize it, they put an intense amount of carbon dioxide in a little gap at the very top. And so that keeps all those bubbles inside. But when you pop the top, what do? So they are allowed to leave via because of the lower pressure conditions on top. We talked about PSIs. We talked about how the gas pressure is very important. If not, you'll be right on the rim. And flat tire. Who's ever had a flat tire? Okay, a couple of us. Okay, it's not fun. One time, I was here my first year teaching. I was here till like 7:30, 8:30 at night. I don't know what it was. And it was during football season. And some of the football coaches waited because they knew whose car it was. But I had a flat tire, and they waited on me. They didn't know who I was. And they changed my tire for me. I thought it was super nice. So anyway, maybe you'll find somebody who'll change your tire for you. Okay. Hairspray. How does that work? Okay, so like when you squeeze the little top. Okay, so liquid gets aerosolized into a gas, possibly. What's inside of it? Those ones that like when you just push the button, they go shh. So it's pressurized with another gas, right? A propellant. Okay, so when it propels it out, it's actually going from a really, really high pressure system inside the can to a really low pressure system, which is outside. So that's the reason it goes out. Well, then eventually, to allow all the pressurized gas out or the propellant out, what stops happening? It doesn't come in where you shake things. You're like, I know there's hairspray in there. I know there's something in there, but you can't get it because there's no more pressure. There's no difference in the pressure conditions, so it stops working. This is not that exact because that's like a pump one. So, okay, and then my football team, we went to like state something championship. My stepdad was a head football coach. My mom was the athletic trainer. So I wrapped people's ankles with her. And then I was water girl for 4 years. Yeah? Okay. So, anyway, we went up to the boonies someplace, and all of our football players just were very ill prepared because we were at this nice condition of a one atmosphere. We went up to like Appalachian to play, and they were like, oh my God, I can't breathe. They just wore out. Why? Well, so they weren't able to acclimate to that as quickly as the other players were, because the other players were used to playing the conditions of low percentage of oxygen in the air. Our players were like, nope, it just didn't happen, so we lost. Okay, I know. Okay, so you guys did that. I'm gonna skip this for now. I'll come back to it. Oh no, yeah. Let me go here first. You guys write down the information about pressure, volume, temperature, and amount. Then we're gonna go to the back and do a quick test. That's like one of the biggest slides. We're going to do some practice. the units that you're writing down are pretty much the most of it, only the units that we'll be using in all of our unit for gases. So make sure that this is like probably one of your most important pieces of notes, because every time we record pressure, you're going to want to be able to adequately convert from millimeters of mercury to atmospheres to kilopascals. In volume, if we're talking about a gas, a lot of times we're talking about liters. Sometimes we do use milliliters, but most of the time we'll be talking about it in liters, because the gases are so expansive. You know, they're boom, 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 they're everywhere like this. Well, that's a lot of volume to talk about, and talking about it in liters just makes more sense. The temperature unit you're going to start to see a lot more often is Kelvin, okay? You must convert to Kelvin if you were talking about gases. So I am sneaky, and I don't give you Kelvin all the time. I give you Celsius. So if I said this gas is at 60 degrees Celsius, what is that in Kelvin? So if I said something was 60 degrees Celsius, you take 60, you add 273, and what would you get?
333.
So 333. And it is 0.15, but a lot of times we will truncate that decimal and just go with and it's not that there's a rhyme or reason for it, it's just people do. It is exactly 0.15, but we generally just disregard that, we round down. And if we're talking about the amount of a gas, we do use moles, and a lot of times I'll be asking you for the grams as well, because I know you guys are champs at stoichiometry. You can convert from moles to grams very easily. So those are the units. Give me a thumbs up when you're done with that. Okay. While my others are finishing, I'll explain to you. I have an egg, as you can see. I also have a flask. Does the egg fit in the flask? No. I'm not magic people, okay? Egg, flask. Okay. I'm going to get that egg in the flask without touching either. Are you ready? I'm ready. Forceps up there. Okay. So I'm just going to prep this up for a second while you guys are finishing. No, I just need you to strike a match. Over here. And then drop the match in here so we don't burn all my precious papers. So just going to prep this up by getting a little ethanol. What's the formula for ethanol? It does start with a C. Because it's organic, right? Can anybody tell me ethanol's formula? C. F means how many carbons? Okay, many elephants play ball. Meth means 1 carbon. F, 2. Pro, 3. Bute, 4. Okay, so ethanol has how many carbons in it? 2. It's got alcohol group. What's the alcohol group? An OH, so it's C2H5, because all the carbons have to have 4 bonds. So C2H5OH. Okay, light this up. Okay, so I got a little combustion happening. I didn't touch it. I didn't mean to touch it. I didn't push it in, guys. Sorry, it was sitting on there sideways. So, as you can see, the egg will not come out. Okay, so why did it go in? Raise your hand. Why did it go in? Why was the pressure outside more than what you say pressure inside? So the fire was using up the oxygen, but what was it making? So shouldn't that just replace it? There is a difference. There's a slight difference. The oxygen does make a little bit more pressure because it's a little bit less. It moves a little faster. I have one more for you. Okay. So this time I'm going to hold it upside down.
Trust me. I've seen it.
Yep. So I'm going to hold it upside down. And I want you guys already know the egg doesn't fit in the flask, okay? You can see it's not fitting in the flask. Is it dropping in the flask? Okay, so it's certainly not going to move upside down, right? Certainly not. Okay, so happy birthday, Mr. Egg. Okay, so I'm not going to push this into there, okay? It doesn't fit. It does not fit. Ever seen Homer continue like this? Okay, so I'm just going to hold the egg as nicely and non-pushy as I can. Didn't push it, did I? So, how'd that happen? Same thing, but where's the pressure pushing? Is the pressure really pushing anyway? It's pushing everywhere. The pressure does not discriminate. It will push up, down, sideways, in, out, whatever, okay? So this one, you can see the pressure is all around us, and it pushed around the kind of the edge of the glass, thank you, Jordan, up, and it pushed the egg into it because there was a difference in pressure inside, meaning the pressure on the inside was lesser and the pressure on the outside was greater. So we did the demonstration with the can yesterday, so I knew you guys would figure that out, okay? Oh, can you just tell me that? I'm not going to break it. I'm just telling you how to get it out. So I can have mechanical force, like that, okay? How can I do it through chemistry? We're in chemistry, people.
Pour some acid in it.
But I light it match in the bottom's got all this area to play. It's not going to
A little bit.
Okay, I could try that. There's an easier way. I'm not changing the egg size. What could I do to the air in here to push it out? Heat it. So what do you think I would heat it with? A Bunsen burner. I just roll the Bunsen burner around it and it goes bloop. I could just shake it, but then the egg would get destroyed. Okay, so let's go back here. I'm going to give us 10 minutes, and that's it. But I have 4 different procedures for 4 different people, so get in groups of 4. Okay, and then when you get back there, let me tell you what to do. Okay, groups of 4, and you should not. Nobody needs. Actually, no. The person using the dry ice possibly needs to need goggles. So, get in groups of 4. You have 30 seconds. You need a piece of paper. You do not need a calculator. You can get a piece of paper. Alright guys, can I have your attention in 5, 4, 3, 2, 1. Syringe. Hold up the syringe. They're going to have to open it up. The marshmallow, you guys will see that. Beakers. 2 beakers. You need 2 small beakers. Jordan is going to want to bring you some warm water. Ice, just general ice, water ice, and then clear. You get a little bit of ice. That's number 1 and 2. Number 3, you guys can read it and figure it out. 4, I want you to hold up an open balloon for me, number 4, and I'll bring you a little piece of dry ice. Okay? You do need goggles if you're dry ice. You do need goggles if you're dry Alright, people, come get the line. Alright guys, please, guys with the marshmallows, you're supposed to open the back of the plunger, pull it off, and then put the marshmallow in, and then take observations when you go in and out of the plunger. Do not push the marshmallow in there where it's not able to get out, and then I'll have to charge you for it already. Those are like $100 each. Okay, they're not $100 each, be careful.
Right, I see. That's the way it could be. Jordan, back. Alright, did you guys do any together? You beat your score.
Any more balloons? Close up dry. Alright guys, you should have all your experiments done in a little bit about 3 minutes. Huh?
Warming up. Let me get an index card.
Guys, finish and make your observations, write them on the on your paper. You know what I'm saying? Yes. Who's on the paper? Who's got number 3? Quick, let's look at Alan. Number 3. Number 3. Stop right and then Okay, raise your hand if you can demonstrate number 3 for us. Try. Oh, that.
Oh, it's really warm.
Give it a second and make more. Sorry. Alright, I'll see you back up at your desk in about 2 minutes. Please clean up your areas. You should have made your observations. You should have made your observations. Leave the dry ice bubbles alone and go to your areas and clean up for me.
This one diffused faster. I don't know why.
All right, guys, clean up your stations. Let's go, let's go. It's right.
It's not.
All right, guys, I'll see you back up here in 5. Let's go. 4, 3, 2, let's go. 1. You keep your balloon. It's yours.
I think expanding quite a bit.
Okay, let's have observations. We have 30 minutes left to do calculations too. I wanted to let you guys play, but I want to make sure we kind of come back together. What were the 2 variables you changed on the marshmallow? Raise your hand, or I will call on somebody if you guys want me to. So the marshmallow, Matt, tell us what the 2 variables that we were using and then what the change was.
The 2 variables?
Yeah, so the variables that we talked about on the last slide. So you changed pressure and you changed. So he told me pressure and volume. Okay, so pressure and volume were the 2 variables you were changing. Add this to your notes that you took on 1 through 4 right here. Whenever you squeeze the syringe, when you input the plunger and you squished it, what were you doing to the pressure? Do we all agree that when you put the plunger in and you pushed it down, the pressure inside, like the little syringe thing, whatever this is, plunger back here, okay? So when you squished it, the pressure increased. Okay, whenever you did that, what happened to the volume of the marshmallow? It decreased. So can you tell me the relationship between pressure and volume? Is it direct or indirect? Indirect. Okay, so we know that it's indirect. In terms of next one, this is a little bit different. This is more about not really gases. This is more about relationships with temperature and speed. Niall, which of y'all's warm or cool water allowed for the food coloring to spread faster? Did everybody's warm water spread faster? Why? Why did the food coloring spread faster? There was not really a reaction. It's more of a mixture. Reactions we stick with chemical. We're sticking mainly with physical right now. Lindsay, tell me what you're saying. So what are you saying that they're? Why are they faster?
Higher temp. The higher the temp is the faster.
Okay, so higher temperature things have higher. What kind of energy? Kinetic energy, and that's why that color spread faster. Color diffused faster. And so if you have a higher temperature, then your molecules are able to move faster because you have more energy, you have more kinetic energy specifically, which is the energy of motion. Cup and index water. Cup and index card, you put the water in it, you flip it upside down, you removed your hand, what happened? The index card stayed, despite the fact that it was inverted, right? So the index card stayed. This is the cup with water in it. The water is trying to push the index card off. What's holding it on? What kind of pressure?
Like atmosphere and like when you close.
Okay, there's a little air in here that's causing maybe a vacuum to form. I'm thinking atmospheric pressure more so though, because you know how the egg went up in the bottle, right? It went up. Atmospheric pressure pushes up, downside, left, right, everything, right? So your index card is trying to come off. The atmospheric pressure is pushing it back on, and it's just counteracting just enough to not really push the index card in the cup, but the water's now starting to push off the cup. So there's a balance. That was kind of cool. And then dry ice in the balloon. What's your relationship? There was 0 dry ice in the balloon. What happened to what was the volume like of the balloon before you put the dry ice in? it was flat, right? We all know it was a flat balloon. So 0, I'm going to put 0 moles of dry ice before. The volume was 0 milliliters. You put the dry ice in. Let's just say we put 1 mole of dry ice in. And we all know dry ice is made of what? CO2. It's a solid carbon dioxide compound, and then it sublimes to gas. So you did not see any liquid state whatsoever. So that was sublimation. What happened to the size of the balloon? Okay, so it's about yay big. Let's call that 200 milliliters. 200 milliliters of gaseous volume. So what's that relationship? Increased moles, increased volume. Is that direct or indirect? That's a direct. When it's up and up or down and down, when they're the same direction, that's called a direct relationship. So a direct relationship between N is what we call moles. Did I have that on the last slide? Moles was N, okay? N and volume. Okay, so let's look at some other relationships and see maybe if we can figure out some of the laws. And these laws you did write down on your reading guide in some way or form, but these are them again. Not all of these examples are the same. We'll kind of talk about these. So I'm going to go in ABC order. Okay, Avogadro's law. This is going to be the different equations you'll use in our gas laws unit, and you'll use these for calculations. So make sure you're writing and labeling these as needed. Avogadro's law. This is not Avogadro's number. This is the relationship. He discovered the relationship like the dry ice and the balloon. What are the two variables that we just used for that description? Moles and volume. Okay, so the relationship is set up like this, and it's an equation. It's math. N1, which is moles, over V1, which is volume, they're related in a direct manner. So I can say scenario 1, like before the balloon was blown up, to scenario 2, when the balloon was blown up, so two different scenarios, equals N2 over V2. So this is the relationship. As N goes up, V goes up. And so it's just like, we call it scenario 1, scenario 2. And we'll go through some examples with that. So what other conditions are staying constant then if we're not talking about them? What are their variables? Right, so this is at constant pressure and temperature, because those variables are not changing. Yeah. And that's just because of the endothermic, of the process of changing the dry ice from solid to gas. What we're saying is the atmospheric conditions are not changing. It probably, truly, would have gotten bigger if it wasn't as cold. And so we're trying to keep all these other extraneous conditions constant. If not, we have to deal with all of them. Dealing with 2 is enough. Dealing with 4 variables might be a little bit more difficult in calculations. Okay, Boyle's law is our second variable. And this is one where, did we do, yeah, the marshmallow and syringe. So in this one, you guys related 2 variables. What were they? Volume and pressure. And you told me they were indirectly related, right? So I divided when they're directly related. So what do you think I'm going to do if they're indirectly related? Multiply, okay? That's an opposite. Opposite of division is multiplication. This one's called P1V1 equals scenario 2, P2V2. And these conditions are at constant what? Constant. So if the pressure is changing, the volume is changing. What has to be remaining constant? Temperature and amount. For N is amount, is moles. So this one's the indirect one. And in this reference, we said as the pressure increased, the volume decreased. And that's why they have to remain constant. This side of the other side has to remain constant. That's why they are inversely related. And everything is common sense. Like you guys have seen this effect. You already know how this works. It's just now we're putting it into mathematical equations. Okay, this was the one from yesterday. And it's a little, yesterday's had a lot of pressure and stuff going on too. But tell me just the basics of right when you started heating up the water. When you started heating up the water inside the can. First of all, it's getting warm, right? What happened to the volume of the gas? It expanded, right? It was water, which was liquid form. Very, very low volume. We have like this much in there. And then you heated it up, and it turned to gas, but the gas started to spread out. When they spread out, it took up the entire container space. And so what we're saying is as you increase temperature, they increase in kinetic energy, and that causes them to spread out. And as you spread out, then the volume would be increasing. So what am I saying? What's the relationship? So the increase in temperature causes an increase in volume. Is that direct or indirect? Direct relationship. So how do we write that one? Is that a division one or multiplication one? Division one. So we're going to write it as V1 over T1 equals V2 over T2. Now temperature in this case has to be expressed in what unit? Say it again? Kelvin. You must use Kelvin. Okay. If you do not use Kelvin, then you're actually going to get the wrong answer because it's not, Kelvin and Celsius are not related through a multiplication system or a division system. It's an addition system. So it's like not even related to our mathematics here. So that's why we cannot use Celsius. We must use Kelvin. So if these two variables are allowed to change, which ones are not changing? Pressure and amount, right? So these two are not, these two conditions are staying constant. And so basically, what I have here, let's say I have a balloon. Let's say I have a balloon. Okay, and I got, let's say it's at 0 or 100 Kelvin. It's at 1 liter. So the balloon particles, they're just bouncing around inside, right? They're hitting the sides of the container. It's at a pressure. It's at a single pressure. When I heat it up, what's going to happen to the gas particles? They what? They try to spread out, right? But what initially, right when you heat them up, what are the particles themselves going to do? Lindsay, you kind of hit this earlier when you were talking about the water. You said hot molecules do what? They move faster, right? Okay, so right now, these are hitting the inside of the container. They're moving kind of leisurely. They're hitting inside the container. What are they going to do when I heat them up? They're going to move faster and they're going to hit more frequently. So let's talk about the frequency first, and then we'll talk about spreading. So if they start to hit more frequently, and the frequency of collision with the container wall goes up, what have you done to the pressure? You've increased pressure. You're not supposed to allow the pressure to increase in this condition, right? The pressure must remain constant. So you're like, okay, the molecules have sped up. They're now hitting the container more. I need to do something to stop them from hitting the container as frequently as they are. What do? You what? You make the balloon bigger. Okay, so we made the balloon bigger because we want to keep the pressure where it is, where it's constant. Because what happens to the balloon if the pressure gets too high? It pops. We don't want the balloon to pop. You know, it's for a kid. We need the balloon to make them happy. I don't know. So we allow the balloon to increase in size. Or maybe the volume gets to 2 liters, but the container is bigger, so the hot molecules, which are now moving faster, they are moving around in a bigger space, so they hit the outside less frequently. So the same frequency of collision over here and here means the pressure is the same. So if you give them more space to play, they hit the sides of the container less frequently. So that's what I mean by these two conditions are changing, making maybe I made this 200 Kelvin or something. They're changing, but the other one is constant, and when the reason it's constant is because usually the volume is changed to make the pressure constant or vice versa. So you gotta kind of talk to yourself on some of these to think about the reasoning behind it. But we've got 2 more laws to talk about, okay? So I always remember Charles's law because Charles went to Virginia Tech. Okay, Virginia Tech, VT. Boyle's law, the B, I don't know, reminds me of a P for some reason. Boyle's law, you're going to need to remember that this person, of course this is a person, right? Everybody comes up with a name for themselves, or a law for themselves. So that's Boyle's law, and Avogadro's law has the B, Avogadro's. So you're going to have to just remember who's who here. Okay, so the last 2, Gay-Lussac's law, which conditions have we not compared yet? Pressure and temperature. Good, because we compared pressure and volume. We haven't compared pressure and temperature yet. So this one, you guys tell me, we kind of just talked through this. If I heat up my particles, what do they do to the container? Well, no, not yet. We're not talking about volume yet. Initially, what do the hot particles do? Speed up. And then when they speed up, what do they do to the container? They hit the container more frequently. What have they just done? Increase the collisions, increases the pressure. So basically, you told me increasing temperature causes them to move faster. And if they move faster, they increase the number of collisions with the container. And if they increase the number of collisions with the container, what does that do to the pressure? Increases the pressure. Okay, so notice I'm not saying anything about volume, because if we're talking about just temperature and pressure changing, what are we assuming is constant? The volume is constant. Okay, so this one is that constant volume and, say again, amount, moles, right? So this one's a direct, you saw me say increase for temperature, increase for pressure. You can see that's a direct relationship. That's going to be P1 over T1 is equal to P2 over T2. And those other variables are remaining constant. Okay, so we've got three main variables that we really talk about a lot. What are those three variables? Volume, temperature, and pressure. Moles is only in one of those equations, so it's important, but it's one of the lower priority ones. So if I'm going to now combine them, I want you to look at Charles's law, Boyle's law, and Gay-Lussac's law, and see how we can combine this into one big law. Say again? P times V, which encompasses whose? Whose is this? Boyle's over T. If I cover up the V, whose is that? V over T. Gay-Lussac's. If I cover up the P, then it's Charles's. You can see them all in one. I like this one the best because, like I just covered up, if I cover up one, I'm saying that is remaining constant. So if I cover that up, I'm like, oh, if I'm reading a problem and I say pressure and temperature noted, and it says volume is constant, you cover it up and you got Gay-Lussac's law. If you say pressure and volume are changing and temperature is not changing, you cover it up and you see Boyle's law. Yeah. I think they just figured it out. They're like, hey guys, we actually just have one law we're working with here, but we're going to name everything else after ourselves too. I don't know who came up with this. It's just called, maybe his name was combined. That would be weird. Okay, and this is assuming constant what? Moles, right? Constant moles, because that's the variable that's not included here. Okay, so we have a bunch of laws to work with. Let's go through a couple problems related to this so that we understand how to read the problems and understand which variable is being given, so we can reflect and say which law should be used. And that's, oops, I did that. I'll get to this pressure stuff tomorrow. These are like pictures of how to depict pressure. Okay, this is number one on the back of your sheet that you were using yesterday. I want you to keep this part because on the back you've got some problems we're going to work through. So number one, that whole section 1 through 5 is regarding Boyle's law. And I'm labeling them for you right now, but I want to walk through how do you figure it out from the problem, because I will not be labeling them. This is Boyle's law, guys. I want you to know how to use your laws or the questions, find what you need. So on this question here, you're just going to start a next sheet of paper. This is called gas laws 1 through 16. So there's 16 questions we're going to work through. We're going to go through probably 5 right now. Ready? Not yet? Okay. So I'm going to model how I think you should set up each of your problems. Okay, here we go. When you're reading, I want you to pull out the information one piece by one piece, label it with the variable it's describing. So at 700 millimeters of mercury, stop. What kind of variable is that? That's what? That's pressure. So right now you're going, I know millimeters of mercury is a unit of pressure. This is a P. Okay, so I'm going to write that down here because I don't want to have to reread this question 500 times. Ain't nobody got time for that. This is a pressure. 700 millimeters of mercury. Okay, I got 2 words in. Great. A sample of hydrogen has a volume of 500 milliliters. What variable is that? Volume. So I'm just going to put V down here for volume. If you do it like this, the law will scream at you and go, use this law. Okay, it helps you see the variables much better. So that's 500 milliliters. If the pressure is decreased to this, what is this? Stan? That's another pressure. Oh, so we're given one pressure, and we're given another pressure. Do you see that that's P1 and P2? Okay, so that's pressure, and this is another pressure, 538 millimeters of mercury. What will the volume be? So question, volume. Say it again. Are the answers are on there, right? Oh, you do see the answers on. Okay. Give me a second. I will need to set this up because I'm not done with the work yet. So if you see that you're given two pressures, so two different scenarios, and two volumes, but one of them is unknown, we're going to call that the two pieces of information given together are labeled the same scenario, and the two pieces of information are labeled the second scenario. So the question here is, first, what are the variables given? Boom, got it done. Second, what is the law we have to use? Boyle's law, which is what? P1 times V1 equals P2 times V2. What are we solving for here? V2. So I want to see your setup, your law, your rearrangement of your law before you plug in, which is, what do I need? I need to isolate V2. So I need to divide by, what am I dividing by? By P2 on both sides. Okay, this is algebra. You're taking your V2 alone, so I had to divide by P2 on both sides. So what I have is this left right here. V2 is equal to P1 times V1 over P2. So I'm just going to write that down here for myself. You don't have to necessarily rewrite it, but it's there. Now, after I've rearranged my variables, now I'm going to plug in, because if you plug in at the beginning, sometimes people mess up. Okay, so I'm just trying to get you to the point where you plug and chug and we're done. What's pressure 1? I hear you, 700 millimeters of mercury. What's V1? 500 milliliters. What's P2? Millimeters of mercury. Good. So if these two pressure units were different, you would need to convert to one pressure unit. You cannot plug in two different pressure units because they won't cancel. Now, I do this because I want to show you that everything cancels except for, so the millimeters of mercury and the millimeters of mercury will cancel. The only unit not canceling is milliliters, and that's what volume can be recorded in, so that means you're right. You've set it up correctly because the unit should agree with the variable being asked. So what's the answer here, James? Can you tell me the answer? 651 milliliters. Because the pressure units canceled, milliliters are left. Okay, so that's how you set up that question. Let's go to another one. Let's go to the next section. So skip some space for 2 through 5. Let's go to number 6. So I want you guys to read it and then tell me what the variables are that it's pointing out to you. Number 6. So now, what's the first variable given to you in number 6? 100 milliliters, and what else? Temperature 273 Kelvin. So I was nice and gave you Kelvin this one, right? Melanie, what else is told to you? So when you said what volume, I'm putting question mark on volume, and temperature is 300 Kelvin. And these kelvins are good to go. Then I see that the first scenario was given to get collectively together. The second scenario was where the question is falling for us. So this one's a little different to set up. What is the law, Maddie? Charles' law. So can you tell me the formula for that? Okay. So I'm not sure what you guys call it nowadays. I call it cross multiplication division. Some people call it floppy dot chop. Some people call it bow tie. So how do you guys rearrange to solve for V2? Because V2s are question. We want to get that by itself. What do you do to manipulate this? Bow tie? So what does that mean? Can you say that? Describe that. Hold on. Don't plug in yet. How many variables? Just variables first. So you basically multiply by T2 on both sides, right? So if you see that T2 needs to get away from V2, you're going to multiply by T2 on both sides. and T2 cancels on this side, and you're just left with V2 is equal to T2 times V1 over T1. So that's right there what I'm going to be plugging information into. Thank you. So V2 is equal to T2 times V1 over T1. It's very important to label these, right? Because once you start rearranging your variables, you're going to not maybe plug things in correctly. So what's going on top? What's T2? 300 Kelvin. See, you know how to label it because you won't know what T2 is. V1, 100 milliliters over 273 Kelvin. Do not calculate yet. I know some of you guys may have, but let's just think about this first. Logically, what should happen to our volume? We've taken our temperature and we've done what to it? Increased it. You know, if temperature increases, what happens to the particles? Immediately when you increase the temperature of our particles, what do they start to do? They speed up. They're beating the side of the container now, right? Oh no, the pressure is increasing. What do I have to do to offset that? Increase the volume. So we all understand that temperature increasing should cause the volume to also increase. So if you always think about that, you're like, okay guys, it should increase. Let's make sure our calculation works. Does it? Yeah, what's the calculation? 110? 111? Did you round? It rounds 110? Okay. Milliliters. And so that should be our V2, and then you're double checking the increase from 100, it went to 110, yep, it did. So that kind of is a safeguard to help make sure you're good. And then again, our temperature units had to be in Kelvin, they both cancel here, leaving us in milliliters. Okay, let's do 14. Scooching on down. Let's do a combined gas law. Read 14 and write down your givens. If you're good to go, please set up. I'm seeing a couple people struggle a little bit. Let's introduce this real fast. You guys pulled 5 pieces of information out of the problem. I'm thinking most people are start plugging it in. So let's label these real quickly. It said that these 3 were all together. It's talking about volume of this volume, 20 milliliters, temperature of 27 degrees Celsius. Right now, what do you know you need to do to that? You need to convert it to Kelvin. Do not plug Celsius into your gas law. So let's go ahead and add 273 to that. What is that? 300 Kelvin. Good. This is our first pressure, 800 millimeters of mercury. And so that's 111. And then they said we're allowing the volume to expand to 43 milliliters. That's our V at this temperature of 50. And then you said 50 degrees Celsius. Oh no, you must express that in Kelvin. So what is that in Kelvin? Good, 323 Kelvin. And our P2 is what's being asked of us. So before I start plugging everything in, let's rearrange our variables. So we have P2 by itself. So all of this information is going to get plugged into what? What law? Combined gas law, right? So P1 V1 over T1 equals P2 V2 over T2. I need to get P2 by itself, and this is where I think people will, you can multiply by T2 and divide by V2. You can do cross multiplication, third time method, however you call it. So do you guys usually multiply these by each other? Yeah? So that's P1 V1 times T2, and you set that equal to this side, right? P2 V2 and T1. I'm just trying to give you a method here. If you need, this one's got 6 variables in it. So they're equal to each other. So then how do you isolate P2 by itself? Divide by what? Yep, so get P2 by itself, V2 and T1 need to be divided by on both sides. And that gives you P2 by itself, because those two variables will cancel. So when you plug everything in here, P1, V1, T2, V2, and T1, you're going to see everything cancels except for what unit? What unit shouldn't cancel? Millimeters of mercury, right? Millimeters of mercury should be our only unit remaining, and that will be the factor, okay? So I'm going to start plugging in here, and you guys do the same and calculate. P2 is equal to sorry. So really, it's this part right here where you administer your credit for the plug-in process with your units and all. So the units of millimeters of mercury will remain. Milliliters, that's V1 and that's V2. Kelvin, T2 and T1 cancel. Millimeters of mercury are remaining. Anybody got me here? Oh my God, okay. All right, guys, 1 through 16. We've done 3 of them. Don't tell everybody about the eggs. These are my surprise. Okay. So I'm meeting.
I think we should pass it.
Oh, yeah.
I just realized I was tutoring to it.
Bye. Oh my God. I was joking. You just got all that. You just got all that? Okay, good. I was like, I hope you weren't just like taking them out. You know?
No, we got an entire kitchen to get with like these.
Where did you guys get this? Oh, okay, okay.
Actually, Sarah did it, so.
Nice. Oh, she gives me a receipt. Okay.
Oh, you want to just like throw away the
There for you. Yeah, go for it.
If we find a earring back on the ground, it looks like the end of the swirly end of the screw.
Okay, I'll switch it here. Bye. Bye, guys.
I'm sorry.